Hello everybody, welcome back to Math 245. This is lesson 14. This is a continuation basically of lesson 13, which we did on Wednesday, all about these feasible regions, which we learned about last time. And today we're going to go a little bit deeper into these feasible regions in order to optimize, which means to maximize or minimize a given function. So first we have a definition. The vertices or corners of a feasible region, they are known as critical points. So anywhere I have a corner or some sort of intersection, these are called the critical points. And the maximum or minimum of our function will always occur at our critical points. But we'll get to that later. In the first example, we have our critical function here, p of xy is equal to 15x plus 6y. And we want to maximize it, make it as big as we can. But this function is subject to all of these constraints. And when we graph all of these constraints, we get what is known as our feasible region. So I first need to graph my feasible region. That's my first step. So let's go ahead and do that. I'm going to make this first one in blue. We have x plus y is greater than or equal to 2. And if I subtract x from both sides, I get y is greater than or equal to negative x plus 2. So I have my y-intercept of 2 and a slope of negative 1. So this graph will look something like this. And now I need to decide which of the regions I want to shade in. So if I test my favorite point, 0, 0, I get 0 is greater than or equal to 2, which is not true. So that means that I'm going to shade the region that 0, 0 is not located in. So let me do that. So it will be this region up here. Okay, next I need to work on my second function. I'm going to do this one in red. So we have 2x plus y is less than or equal to 8. So if I subtract my 2x over, I get y is less than or equal to negative 2x plus 8. So my y-intercept is 8. My slope is negative 2. So my function looks something like this. Now I need to decide which of the regions to shade. So I'll test 0, 0. And I get 0 is less than or equal to 8, which is true. So I want the region that contains our point 0, 0. So that will be this region right here. All of this. So far, our only overlap is this kind of purpley triangle piece on the middle. Okay. The next thing I need is my next equation, this guy. So I have x plus 2y less than or equal to 8. And I need to get it into y equals mx plus b form. So I subtract x from both sides. And I get 2y is less than or equal to negative x plus 8. And then if I divide 2, I get y is less than or equal to negative x over 2 plus 4. So my y-intercept is 4. My slope is negative 1/2 x. So my slope will be something like this. And then I need to test my point. You can test any point, but 0, 0 is my favorite since it's the easiest one. So when I plug in 0, 0 into this equation, I get 0 is less than or equal to 4, which is true. That means that the region containing the point 0, 0 is what I want to shade. So that will be all of this. So far our feasible region is this triangle that's between the red and the green and the blue parts. But I have two more constraints. My first constraint is, well, I have two that are basically the same. Y and X both have to be greater than or equal to 0. So if I have X is greater than 0, I know that I am going to be to the right, of the y-axis. So I'm going to be on this side of the y-axis for X greater than 0. And for Y greater than or equal to 0, I'm going to be above this line, the x-axis. And now we have our feasible region. So our feasible region, let's look at the critical points on our feasible region. So it's this kind of pentagon shape in the middle here. So our corners of this feasible region is right here, 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 and here. Those are the corners of our feasible region called the critical points. So I need to identify the critical point. So I'm going to label these 1, 2, 3, 4, and 5. So the first one, number 1, is the y-intercept of the green line. And the y-intercept of the green line, if I look back up here at my green line, is the point 0, 4. So this is one of my critical points. The second one, point number 2, is the y-intercept of my blue line. And the y-intercept of my blue line is the point 0, 4. The third one is the x-intercept of my blue line. Oh gosh, I just did a bunch of stuff. I'm so sorry. Still the same. I just accidentally erased. There we go. Okay, so the third one is the x-intercept of blue. So to find the x-intercept, we need to set our equation, this guy right here, to set y equals 0. So I get 0 is equal to negative x plus 2. I want to solve for x. So if I add x to both sides, I get x equals 2. So this point right here is the point 2, 0, number 3. Point number 4 is the x-intercept of the red line. So I need to set y equals 0 on my red line. I get right here. So I get 0 equals negative 2x plus 8. If I add 2x to both sides, I get 2x equals 8. So x equals 4, and it gives me the point 4, 0. So I have one more point, this point number 5, and point number 5 is where my green line and my red line intersect. So number 5 is where green and red intersect. So I need to set my green line and my red line equal to each other to solve for the x value. So I am going to set my red line, negative 2x plus 8, equal to my green line, negative x over 2 plus 4, to see which x value they intersect at. So I'm going to add x plus 2 to both sides and subtract 8 from both sides. This gives me negative 3 halves x equals negative 4. So now if I divide both sides by negative 3 over 2, negative 4 divided by negative 3 over 2 is equal to 8/3. Now I need to find my y value. I can find my y value by plugging this x value into either one of those equations. The red one looks easier to me. So y equals negative 2x plus 8 equals negative 2 times 8/3 plus 8, which is actually 8/3. So this point is 8/3, comma 8/3. That is my last critical point, number 5. All right, so I have listed the critical points here. We have, let's see, 0, 4, this is point number 1. Point number 2, oh, wow. I put the y-intercept of the blue one as 0, 2, didn't I? Or 0, 4, it should be 0, 2. Okay, so this is number 2. This one is number 5. This is 3, and this is 4. So now what I'm going to do is I'm going to plug in each of these critical points, the x value and the y value, into our function p. So remember, p of xy equals 15x plus 6y, this function way up here. So I'm going to plug in my x value and my y value for each of these critical points. So here in the first one, I get p of 0, 2 is equal to 15 times 0 plus 6 times 2, which is equal to 12. In my next one, p of 0, 4 is equal to 15 times 0 plus 6 times 4, which is 24. P of 8/3, comma 8/3 is 15 times 8/3 plus 6 times 8/3. Well, 15 times 8/3 is equal to 40. And 6 times 8/3 is equal to 16. So this is 56. P of 2, 0 equals 15 times 2 plus 6 times 0, which is equal to 30. And finally, p of 4, 0 is equal to 15 times 4 plus 6 times 0, which is equal to 60. And we want to maximize this function, so I need to see which of these values is the greatest. Well, it's 60. So the objective function has a maximum value of 60 at the point 4, 0. So the first thing that I did here is I graphed the feasible region. Then I labeled each of my critical points. That's the corner points of the vertex of any time any of these graphs intersect. Then after I found my critical points, I plugged each of them into our function p of xy in order to, in this case, find the maximum. So that is what I did. Let's do another example. I want to maximize a different function now. P of xy is equal to 4x plus 28y, subject to all of these constraints. So I first need to graph the feasible region. My first graph is x plus y greater than or equal to 1, which is y is less than or equal to negative x plus 1. So my graph has a y-intercept of 1, a slope of negative 1. So my graph looks like this. I'm going to test a point to see which region I shade. I get 0 greater than or equal to 1, which is not true. So I graph the region that is not containing 0, 0. So that will be this region up here. Okay. Next, I look at 3x plus y is less than or equal to 9. 3x plus y less than or equal to 9. When I subtract 3x from both sides, I get y is less than or equal to 9 minus 3x. So my y-intercept is 9. My slope is negative 3. So my graph looks like this. To find which region I shade, I test 0, 0, which gives me 0 is less than or equal to 9, which is true. So I need to shade in the region that has 0, 0 in it, which will be this one. So far my intersection is that little triangle region. All right, my next equation is x plus 3y less than or equal to 9. If I subtract x from both sides, I get 3y less than or equal to negative x plus 9. And dividing by 3 gives me y less than or equal to negative 1/3 x plus 3. So my y-intercept is 3. And my slope is negative 1/3. So like this. I'm going to test 0, 0, which gives 0 less than or equal to 3. That's true. So the region with 0, 0 is the one that I want. So my region so far is this little triangle in the middle. And then I have the constraint again that x and y are both greater than or equal to 0. So I'm going to be above the x-axis and to the right of the y-axis. So I can see here that my critical points are this one, we'll call it 1. This one is 2, 3, 4, and 5. So both in this example and in the previous one, we got kind of like a pentagon shape. It won't always be a pentagon shape. Sometimes it will be a triangle. Sometimes it will be something totally different. It just so happens that they look pretty similar in both of these examples. Okay, so I need to identify now my critical points. So number 1 is the y-intercept of the red line. So that is, if I look at the red line, the point 0, 3. Number 2 is the y-intercept of the green line. If I look at the green line, that is the point 0, 1. Point number 3 is the x-intercept of green. So I set my green line, I set y equal to 0, so I get 0 equals negative x plus 1, or x equals 1. So this gives me the point 1, comma 0. The point number 4 is the x-intercept of the blue line. That gives me the point, if I plug in y equals 0, I get 0 equals 9 minus 3x, or 3x equals 9, so x equals 3. So I get the point 3, 0. And finally 5 is the intersection of red and blue. So I set these two lines, red and blue, equal to each other to find the x value. So I have 9 minus 3x equals, that's the blue line, negative 1/3 x plus 3. That's the red line. So I'm going to add 1/3 x to both sides and subtract 9. And I get negative 2 2/3 x equals negative 6. So if I divide negative 6 by 2 2/3, I get x equals 2.25. To find the y value, I plug this guy back into either one of the original equations. So y equals, I'll do the blue one, 9 minus 3 times 2.25, which is also 2.25. So this critical point is 2.25, 2.25. So now I have all of my critical points that I've listed here. Let's see, this one is 0, 1, number 2. This one is number 1, number 5, number 3, number 4. So I plug in all of my critical points into my P of xy. Remember, P of xy equals 4x plus 28y. So P of 0, 1 equals 4 times 0 plus 28 times 1, which is 28. P of 0, 3 equals 4 times 0 plus 28 times 3, which is 28 times 3 is 84. P of 9/4, 9/4, or 2.25, 2.25 is 4 times 2.25 plus 28 times 2.25. This is, well, 4 times 2.25 is 9, plus 28 times 2.25 is 63. So we get 72. P of 1, 0 is 4 times 1 plus 28 times 0, which is 4. And finally, P of 3, 0 is equal to 4 times 3 plus 28 times 0, which is equal to 12. In this case, I want to maximize my function. My maximum value here is 84. So I say that my objective function has a maximum value of 84 at the point 0, 3. So this is what it means to find a maximum value of an objective function. We first graph the feasible region, and then we find our critical points, and then we plug in all of our critical points into our objective function to find the maximum value. All right, go ahead and go on over to lesson 15. I will see you there.